In this video, we are going to talk about the goodness of fit test after we learn about the chi-square distribution from the last chapter. The goal in this video is to use the chi-square statistics for hypothesis testing with the qualitative data or categorical data. And one example of that is about the weather. This is a qualitative data. When you were asked to ask about the weather that you like, you may answer that you like the sunny, cloudy, snowy, rainy, windy, and so on. So these are the qualitative data. Qualitative is different from quantitative, which is the numerical value. This is not a numerical value, but this is about the letter, the word, and so on. Now let's consider the problems we have here. So when I want to determine whether a coin is fair, and we can do this by tossing the coin a number of times, and then we compute the sample proportion p hat of the heads, and then we can use the test for a population proportion from the last chapter. And if the coin is fair, we expect to get the proportion of the head to be 50% and the proportion of the tail to be 50%. And you can form the hypothesis, the null hypothesis and the alternative hypothesis by letting the proportion equal to 0.5. This is the original assumption. So we assume that the proportion is equal to 50%. That means you can get the head or the tail when tossing a coin, and the chance of getting one of them is 50%. And if your null hypothesis is not true, then they may be different, right? You could get the tail or you could get the head. So your proportion is different from 0.5 or it is different from 50%. And because the population proportion test is only deals with the two outcomes only, the head or the tail. Remember, the population proportion test is the binomial distribution, right? You only work with two outcomes, head, tail, or success of failures. So what happens if I want to determine whether a die is fair? Now the die has 6 outcomes, namely 1, 2, 3, 4, 5, and 6. There are 6 outcomes. So for a die to be a fair die, the probability of getting any number 1 through 6 would be 1 over 6. So the probability of getting number 4, there's only one number 4 out of 6 choices, so 1 over 4 for each number. 1 over 6 for each number. And therefore, now you can also form the null hypothesis and the alternative hypothesis by letting the null hypothesis to be all the proportion or all the probability of getting any number 1, 2, 3, 4, 5, and 6. They are equal to 1 over 6. And then the alternative hypothesis is that not all of the probability of any one of these equal to 1 over 6. That means there is 1 or 2 or 3 of them, the probability of getting that value is not equal to 1 over 6. So this is the conditions against the null hypothesis H naught, because you are looking for the die to be fair, so you want all the number to be equal to 1 over 6 for the probability for each number. And you see that here we have 6 different outcomes, and you cannot use the population proportion test as before, because there was only 2 outcomes for the proportion test, and in this case we have 6 outcomes, and therefore you have to use something else to perform the testing, which is the goodness of fit test or the chi-square test in this videos. Alright, so now let's go over the goodness of fit test. Suppose that now we roll a die 60 times. Okay, so n equals 60. This is the number of the trial. So we roll the die 60 times. And then we obtain the following. This is the outcome of number 1, of getting number 2, of getting number 3, 4, 5, and 6. And then the observed value. So out of 60 times, there are 12 times that you would get number 1. There are 7 times that you would get number 2 of the dice. There are 15 times of there's 15 out of 60 times that you roll the die, you would get number 4, and so on. So this is the observed frequencies. Now to test for the null hypothesis H0 here, we also need to compute something called the expected frequencies. The expected frequency is the mean counts that would occur if the null hypothesis is true. So let's see what does the expected frequency in this semi-sample. So the expected frequency is calculated by getting the number n multiplied by pi, where n is the total number of trials, and pi is what? Pi is the probability of getting that outcome I. So for example, I am looking for the expected value of the semi-sample here. The second row we just saw, they were the observed values of number 1, 2, 3, 4, 5, and 6. And because pi is equal to 6 in this 1 over 6 in this case, because pi is the probability of getting any of the number if we assume that the null hypothesis is true, which is 1 over 6, and 1 over 6 multiplied by n, in this case your n is 60 because there are 60 trials. So 60 times 1 over 6 is 10. So 10 is the expected value for all of the outcomes 1, 2, 3, 4, 5, and 6. Now if we want the null hypothesis to be true, that means you want the observed frequency and the expected frequency to be very close to each other, right? You want the observed one, the expected to be approximately equal to one another if H is not was to be true. So the larger the differences between the observed and the expected frequency, then there would be more evidence to against the null hypothesis. And we can use the chi-square statistic to measure how large the differences between the observed and the expected frequency. And the chi-square statistics is defined to be the summation of O minus E, the summation square over the E. And your O1, O sub 1, O sub k, this is just the observed frequencies from the second row. So for example, O1 is the observed frequency of the outcome of number 1, and so on. And then E is the expected frequency, again, from 1, 2, 3, 4, 5, 6. And K, this is the number of the calories here, in this case 1, 2, 3, 4, 5, and 6. And then because we are using the chi-square statistic, we also depends on the degree of freedom. So there are K minus 1 degree of freedom for the chi-square statistics. And make sure that when we want the null hypothesis to be true, all the expected frequencies, they need to be bigger than or equal to 5, and make sure we have to check this requirement before proceeding to the next step in the testing process. Now let's take a look at this example for how to use the chi-square statistic to perform the testing, the goodness of fit test. Okay, so a poll conducted by General Social Survey. They asked 1,155 people whether they thought that people with high incomes should pay a greater or smaller percentage of their income in tax than the low income people. And the results here are presented in the following table. So we have the category Anytime you see that there's a calorie, then you should know that you should apply the chi-square statistic or the goodness of fit test to solve the problem. So we have 4 of them. Pay much more, pay somewhat more, pay the same, or pay less. And then for each category, we have the number of the people that answer the survey or choose that selection. And if you add all of them here together, all the observed frequency together, you should get a total back of 1,155 people. Now, 5 years earlier than this survey, it was determined that 18.5% believe that the rich should pay much more. So pay much more is 18.5% 5 years earlier. And then 32.9% believe they should pay somewhat more 5 years earlier. 41.2% believe they should pay the same. And 1.1% believe they should pay less. So the question here is, can we conclude that the current percentages here differ from these? So can you conclude that the two data, the one 5 years earlier and the one now, are they the same? Are they different? And can you conclude that they differ from one another? So we use the alpha, the significant level, to be 0.05 for the testing. Okay, so this is belonging to the calorical data or qualitative data, and we can apply the goodness of fit test, which is the chi-square distribution, and to perform the testing. So the null hypothesis here is that we assume the null hypothesis is always the original assumption. So the original assumption of 5 years before that, they assume that for the calorie number 1, it is 18.5%, and then pay somewhat more is the second calorie, or it was 39.2%. So I placed that for the null hypothesis H0. The P1 is 18.5% or 0.185. So make sure all the percentages we convert it back to decimal values. And then if the null hypothesis, they are not true for all the percentages here, then the alternative hypothesis means that some of the probabilities, some of them here, they are different to the value specified by the H0. That is now, the value now, some of them, they are different from what as stated here on the null hypothesis. And then K is 1, 2, 3, 4 because we have 4 calories. 1, 2, 3, 4. So here is the null hypothesis, and also the alternative hypothesis. So we state the null and the alternative hypothesis. So we are testing between these two. If we reject the null hypothesis, that means some of the probabilities, they are different from the 5 years earlier. If we do not reject, then there's a high chance. So now let's check the expected frequency. Make sure this is a very important requirement. Now we have n to be 1,000, 1,155. Those are the number of the people that we did a survey. So the expected frequency is equal to n times p. N is a total number of the frequency. And then P1, P2, P3, P4, those are the probabilities from the null hypothesis, if the null hypothesis was to be true. So we take each of the null hypothesis probabilities, P1, P2, P3, P4, we multiply to the n to get the corresponding expected value for each of the calorie number 1, 2, 3, 4. And we confirm that all the 4 values, they are all bigger than or equal to 5. And therefore, we can proceed to the next steps in the testing procedure. The significant level is alpha equals 0.05, so this is predetermined for you, so you don't have to worry about how to choose this value. And the next thing is to compute the test statistics. This is what? This is the testing that you the formula that you saw here. The chi-square is equal to the summation of all, which is the observed value, minus the expected value, and then over the expected value square. Now this is the summation notation. That means you add all of them. You add all of the value from k from the 4 calories 1, 2, 3, 4 together. The summation. And you see that this is the formula. We have 4 calories from 1 to 3, 4. So we go from I from 1 up to 4 max, and we can expand the summation into the summations of 4 of them. So O1, E1, E1, and then we increase to 2 and 3 and 4 and so on. And you can see here the O1 is the observed value. The observed value is right here. O1 218. Expected value 1 is 213.675, and then divide by the expected value. And then on the numerator, make sure that you square. And then do the same thing for the rest. O2, O3, O4, O3, and O4, and then add all of them together. This is the test statistic, which is 10.261. And after we find the test statistic, we next find the critical value. And in order to find the critical value, you also need to find the degree of freedom, which is k1 at 4. And k is the total number of calories. In this case, 4 subtract 1 is 3. And to find the critical value, we go ahead and we use the chi-square distribution table. You can Google the chi-square distribution table. They have all the table available on online, or you can find this in the back of your textbook. But this is one of the example for the chi-square distribution table. Now, the significant level alpha is 0.05. That is the area to the right of your chi-square. So we go from 0.05. This is the alpha level, and you have 3 degree of freedom, df degree of freedom, and that should be this number. 7.815 is your critical value. Now there's a rule. So if the test statistic is inside the critical region, we reject the null hypothesis. If the test statistic is not inside the critical region, we fail to reject the null hypothesis. In this case, if you draw the chi-square, first thing is I label the critical value, which is the one I found by the table here, 7.815. And then my test statistic earlier from the chi-square formula, I got 10.261. And that 10.261, of course, 10.261 is after 7.8. And therefore, this point is inside the critical region, right? This one is the critical region. And if you are inside the critical region for the test statistic, then you reject the null hypothesis. That means we reject this hypothesis right here. We reject this hypothesis. That means we will support the other alternative hypothesis. That means some of them may not be equal to one of these values. Alright, so because the test statistic is inside the critical region, we reject the null hypothesis. So conclusion, the distribution of the opinions on these problems, they are changing during the 5 years prior to the survey. It should be 5 years, because for the problem it is 5 years earlier. So they are changing. They are not stay the same. Right? They are different. Now, if you if you are using the TI-84 or Excel, then we can also be able to find the p-value. And for the p-value method, it's very simple. If the p-value is less than alpha, we reject the null hypothesis. If p-value is bigger than alpha, we do not reject the null hypothesis. Now let's try to use a TI-84 and confirm that we get the same conclusion with the critical value method. Now if you are using the TI-84, we press on start, we go to test, we scroll down, you want to find the chi-square, the goodness of fit test. Now they require the observed and the expected value. So let's go back to the observed value. Okay, your observed value is right here. We need to input that into the list first. So let me use start and then edit, and then my list L1 is my observed value, 15. And then my expected value is my column number L2. So let me go down to my expected value E1, E2, E2, and E4. So I go ahead and I enter 213.675, 452.76, 475.86, 12.705. So we need the one column for the observed values and one columns for the expected frequency. And now that's L1 and L2. Now let's go back to start, test, goodness of fit test for the chi-square. Observed value is L1, expected value L2. Degree of freedom we saw here is 3. And then you want to hit the calculate. Now it's display everything for you. It display the p-value for you. P-value in this case 0.016. If you round it to two decimal places, then it's 0.02, right? 0.02, and 0.02 is less than the alpha. So p-value is less than alpha. P-value is less than alpha. P-value is less than alpha. Then we reject the null hypothesis, which is the same conclusion right here. We reject the null hypothesis. So getting the p-value from the TI-84 is a quicker way, and you still end up with the same conclusions. Now we can also use Excel to do the testing if you don't have the TI-84. Again, if you are using Excel, we still need to apply the observed value and the expected value that you used in the two columns earlier. So how about let me just put the B column for the L1. This is the observed value or observed frequency. So that's going to be 218, 497, 425, 15, and this is the expected frequency, and that is 213.68, 452.76, 475.86, and 12.705. Now in order to use the testing on Excel here, you press the equal sign and then go to formula, insert function, and choose statistical, and then you would want to look for the chi-square test. Chi-square test, to go slowly here. So chi-square test right here, CHISQ chi-square dot test. So you want to click on this function. Now the actual range, this is your observed value. So you're gonna drag the whole data list, and your expected range is your expected frequency. So you're gonna drag the whole thing here, and then you're gonna press the OK key, and this will return the p-value. Okay, the p-value, and let's compare with what we got earlier. Start test, and then go to the GoodnessofFit test for chi-square, A1A2 degree freedom. Alright, you're gonna get 0.016476. So they are pretty much the same thing. So this is the p-value from Excel, and again, this is less than alpha, which is 0.05, and it's less than alpha. We reject the null hypothesis. So we do end up with the same conclusion, no matter if you are using p-value or critical value, or if you are using the Excel by hand or by the TID4.